When you think about a serious head injury, you probably picture that one single violent moment of impact. But what if I told you that's just the beginning? What if the most devastating damage actually happens silently, in the minutes, hours, and even days after the initial hit? So what is really going on in there? That's what we're going to dive into. We're going to unpack the hidden biological chain reaction that unfolds inside the skull following a traumatic brain injury. It's a process that starts with a bang, but it's the silent internal storm that follows that we need to understand. All right, so to really get a handle on that storm, we have to start at the very beginning. We need to look at the first blow and what it actually means to have a traumatic brain injury in the first place. Okay, so here's the official definition. And the key words here are alteration in brain function. See, it's not just about a cracked skull. A TBI is any external force that messes with how your brain works. And that can be anything from what seems like a minor concussion all the way to the most severe damage from something like a car crash. You know, a really good way to think about a brain injury is like a play with two acts. Act one is what you'd expect, the primary injury. This is the immediate physical damage, the bruising, the bleeding. But then there's Act two, the secondary injury. This is a delayed chemical cascade that ripples through the brain. And frankly, this second act can be way more destructive than the first. This is the silent part of the injury, and it's what we're really focusing on today. So let's pull back the curtain on Act 2. We're going deep inside the brain to see this hidden cascade up close. And believe me, it's a complex and kind of terrifyingly fascinating process. The best analogy for this is a series of dominoes. The first domino is the impact itself. It causes a massive short circuit in the brain's wiring, making neurons fire uncontrollably and release a flood of chemicals. Now, all that chaos sends the brain's metabolism into hyperdrive, creating an energy crisis. The brain cells are just burning through their fuel source, ATP, like crazy. So what happens when the power goes out? Well, the cell's safety pumps fail. This allows toxic levels of calcium to flood in, which then activates enzymes that, well, they literally start to digest the cell from the inside. And that triggers the final domino, a massive inflammatory storm that leads to widespread cell death, long, long after that first hit. So all this cell death and inflammation, well, it leads to another huge problem, swelling. And when the brain swells, it gets trapped inside a very, very unforgiving container. Think of it like a pressure cooker. So there's this concept called the Monroe-Kelly doctrine. Basically, your skull is a sealed, rigid box with a fixed amount of space. And normally, it's perfectly balanced. You've got your brain tissue, your blood, and your cerebral spinal fluid all fitting in there just right. Everything has its place. But after an injury, you try to cram something new into that sealed box, swelling or bleeding. Since the skull can't expand, that new volume has to go somewhere. So it starts to squeeze and crush everything else inside. The pressure just skyrockets. And there's a name for this: intracranial hypertension. It is an incredibly dangerous state to be in because as that pressure builds up, it literally starts to choke off the brain's own blood supply, which, as you can imagine, leads to even more brain damage. You don't have to be a math genius to understand this equation. It's really simple. The pressure inside your skull is called intracranial pressure, or ICP. As that number goes up, the amount of life-sustaining blood that can get into your brain goes down. It's a terrifyingly simple relationship. More pressure inside means less blood and oxygen for the brain cells that are desperate for it. Okay, so if so much of this damage is happening on a chemical, invisible level, how on earth do doctors measure it? How do they decode what's going on inside a patient's head? Well, one of the most important tools is a scoring system called the Modified Glasgow Coma Scale. It's basically a standardized checklist. Doctors evaluate three key things: how the patient moves, their basic reflexes, and their level of consciousness. They get a score between 3 and 18. And the rule is simple: the lower the number, the more severe the brain injury. And what's really fascinating is that this score connects to real physical changes you can measure. For example, a study in dogs found this incredible link. As the brain injury got worse, meaning the MGCS score went down, the dog's blood took longer and longer to clot. It's a powerful reminder that a brain injury isn't just in the head. It sets off a cascade of problems throughout the entire body. So that brings up another question, right? If clotting is affected, what else is? Could we maybe look at the body's overall stress response to get another clue about how bad the injury is? And the answer is a resounding yes. Research shows a crystal clear trend. The more severe the head trauma, the higher the patient's blood sugar is when they get to the hospital. And this isn't random. It's a direct reflection of the massive stress response the body is launching to deal with the injury to the brain. The bigger the injury, the bigger the stress. So, we've looked at the first hit, that silent secondary cascade, the pressure problem, and how doctors try to measure it all. But what's the bottom line here? Why does understanding all this physiopathology matter so much in the real world? This quote right here gets to the absolute heart of it. The research points to a critical window of time. It says that by just 4 to 6 hours after the injury, that destructive inflammatory storm kicks into high gear. From the moment of impact, the clock is ticking loudly. And that's really the whole ballgame. You can't go back in time to prevent the primary injury. So everything that doctors do in the ER and ICU is focused on one single thing: fighting a battle against that secondary cascade. It is an absolute race to stabilize the patient and stop those chemical dominoes from falling before the damage becomes permanent. All right, so let's just quickly recap the most important points here. First, the real fight in TBI is against that delayed secondary injury. Second, that cascade is basically a chemical storm that kills brain cells hours after the initial hit. Third, that pressure cooker effect inside the skull is so dangerous because it can starve the brain of oxygen. And finally, doctors use tools like clinical scores and blood markers to try and see this invisible damage. Which leaves us with a really profound challenge. We know the battle for the brain is so often won or lost in those first few critical hours. So the huge, pressing question for medicine and science is this: how can we get better at fighting that silent secondary cascade? How can we develop new ways to intervene and win?